A quick introduction to Israel himself. He's a familiar face in our conferences. He's made many contributions over the years. And so thank you for coming again with another subject. From memory, this was something which you had hoped to present to us last year, but I think there was a little bit of a delay in getting the authorization and the data ready. So I'm glad that you've been able to come back and do that. Israel, as you probably guessed from his name, is Spanish, and he's also, like some of our other presenters, working in the test center of Airbus Defence and Space. And he's been doing that since 2003. So coming up on 20 years of experience now. And his current position is in the computer vision team in Airbus Defence and Space. And you'll see from his presentation what that means. He's shared some of his work before in different presentations, so I know it's very, very interesting. It says here that unbelievably, he has spare time and he enjoys tennis and cycling. And he's the first of our presenters who claims to have any spare time. So you're a very lucky guy, Israel. So.
Well, today is more difficult. I have a little dog, so it's worse.
Okay, just give me a few moments to prepare your video, and then I'll start playing it, and we'll come back to you at the end. Okay.
Okay. If you let me, I will like to say some words at the beginning.
Sure, go ahead.
Yeah, okay, so thanks Gina and Paul for the invitation. I would like to share this, this is a pre-recorded vision because I participate also in another congress in the ETTC, and the requirement was pre-recorded, so for me it's easier to share with you this video again. And I am happy to share with you because this is the second part of the presentation that I did in 2016. Related to the A400M with cameras on board. So this is the second part of this paper. So I'm happy to share with you, and I hope you will enjoy the video. Okay.
Okay, thanks. Thank I'll set it up and press play.
Okay. Hello, good morning, everyone. Bonjour à tous. Buenos días a todos. My name is Israel Lopez. I am Spanish, and I work in the test center in Airbus Defence and Space. Today, I'm going to talk about trajectories of paratroopers. But first of all, let me introduce myself. Well, I am a software engineer from the University Complutense of Madrid. In 2003, I started working in Airbus Defence and Space. My actual position is computer vision responsible in the test center in Spain. I am a specialist in photogrammetry, simulation, and image processing. I have 2 patents and several papers in technical conferences. I am married and I have 2 daughters. I spend the little time I have left playing tennis and cycle. I hope you will enjoy the presentation. Okay, let's start with the presentation. One important capability of a new tactical aircraft, like the A400M, is the ability to dispatch paratroopers simultaneously from the side doors. It is required to analyze the centerline tendency and resulting paratrooper interactions during simultaneous dispatch. From Airbus Defence and Space point of view, it is essential to analyze this effect in a well-known aircraft, accepted by the nations. In this case, the C130 has been selected as the reference aircraft. To quantify the paratrooper interactions, a series of paratrooper live jumps were performed on a C130, and the trajectories of these jumps recorded. The trajectories of the paratroopers were required to analyze the centerline tendency in the different flight conditions. In this presentation, I will explain the methodology used to calculate the paratroopers' trajectories using photogrammetry techniques and image processing. Before talking about the methodology, I will talk about the flight test means used in this campaign. The aircraft. As I said, it was a C130, the H model from Belgium, with 4 turboprops, all rotating counterclockwise direction and with a maximum paratrooper of 64. The test facilities. The airbase in Francasal, France, and the dropping zone near to this place in Fonsorbes. The parachutes, this was selected, the Advanced Combat Parachute System made by Safran. And the Cinetheodolites, very important. 2 Cinetheodolites located on ground, very in a strategic position, named Tom 103 and 104, and with tracking capability, because these are like a telescope. Let's talk a little about the international collaboration to execute these flight tests. France, with the Direction Générale d'Armement and the Army, they put the onboard support during test, ground support, access to test area and facilities. They put the paratroopers, the medical services in the drop zone, and the manager. Also, the Belgian Air Force, they offer the aircraft and the crew, the parachutes, and the equipment management and preparation. And at least, and not least, Airbus Defence and Space, we coordinate the campaign with the flight test program. We develop the methodology to generate the parachute's trajectories and the methodology for the calculation of the interaction analysis. And now I will talk about the most important part in this presentation, the methodology. The trajectories were calculated by analyzing the recorded images with the help of a software. This software has 4 important topics. This was developed by ourselves. It's based on Python because there are a lot of libraries, and this is a very open language for programming, and there is a big community. And as I said, we are experts in photogrammetry algorithms, and we also use image recognition techniques, for example, for the number recognitions. So, as we are calculating positions, we need an axis reference system. In this case, we use a reference system near to the dropping zone in front Sorbes. So, here you see this is the reference position, the origin, the point P11, and the x-axis is pointing to the east, the y-axis is pointing to the north, and the z-axis is perpendicular to both of these and positive upward. Let's continue talking about the different pieces of this cake. The camera calibration. As you probably know, we need to transform from 2D, the pixels, to 3D in the space. So we need to use cameras, and these cameras are not perfect. So we need to know the different parameters. The name is intrinsic optical parameters. So for example, typically the principal point is the center of the lens, and we need to know which is the offset in the sensor. Okay, so because typically there is a little offset between the center of the lens and the center in the sensor. Okay, and also the focal length is the distance between the sensor and the lens. This is something that we need to know to transform from 2D in the image to 3D. And also there are other parameters very important. No? In the cameras, typically they produce aberrations. For example, in this image, you can see that there is some kind of curvature. So we need to rectify these images to another images without these aberrations. So for this, we need to know some coefficients to transform from these kind of images to these ones. The second thing we need to know about cameras is the position and the angles. We know the position because these Cinetheodolites are in static places, and DGA calibrate this position, and they gave to us the positions. But we need to know also the angles, because these Cinetheodolites are following the parachutes. So in this case, the pitch and the yaw angles are in this part of the image. So we need to develop an image recognition algorithms to obtain these numbers. The roll angle is 0, and one important thing is we need to recognize this with a 100 percentage of accuracy. Okay, and we need to know also these numbers during all the frame, because these are changing all the time. Here we have a big problem. The Earth is not plane. Yes, I believe in Aristotle and Cristobal Colon. So, due to the distance between ton 103 and ton 104, the axes are not completely parallel. You can see here that, for example, the Y1 and Y2, these are pointing to the north, but in this latitude, you see that these are not parallel. So a simple translation is not enough. So to solve this issue, it is needed to transform pitch and yaw angles to the same reference system. In this case, we will use the R2. So just to give you some intuition, because there are a lot of formulas behind this, and you can find this in the paper, I will give you just two ideas. So the first step is to transform the vector from reference 1 to geocentric system, and the second step is to transform vector from geocentric to reference R2. So I would like to thank to DGA for all their support in this part. As you probably know, flight tests are very expensive, so I recommend to do simulation as much as possible. So in this case, we simulate the scene and we generate artificial images very representative of the real Cinetheodolites, and we use these images for the validation of the methodology. A preliminary study was done to evaluate the accuracy of the trajectories, generated using internal photogrammetry algorithms and just taking into account as error the 2D position of the object to track and the position of the camera. The following inputs were used for the study. The standard pixel error for the tracking as 1.4 pixels, the standard position camera error as 1.01 meters, and the standard angle camera error as 1.01 degrees. And these errors are introduced into the photogrammetry algorithms over 1,000 iterations, and the results are compared with the known theoretical position, producing the following errors in the outputs. Standard position paratrooper X about 0.16 meters, standard position paratrooper Y 0.13 meters, and standard position paratrooper Z about 0.1 meter. So we can see that the error is small, so it's perfect for our objective. So let's talk a little about the calculation method of these trajectories. First phase is the 2D tracking. We need to extract the 2D coordinates of different points. In this case, the lateral points, these lateral points, and the head of the paratrooper. We apply Lucas-Canat method for the tracking, and we calculate the centroid automatically. We calculate 6 seconds of trajectories. The trajectory starts as the paratroopers jump and covers the stabilization of the parachute. This is when the parachute is vertical. Second phase, the 3D calculation. This is a photogrammetry process, okay? We need to rectify the 2D coordinates with the camera calibration. We need to calculate the director vector from camera to these calibrated 2D coordinates. In this case, the vector of from camera to the head, and from the vector from the camera to the centroid. And the last part of this phase is the calculation of each camera's 3D lines of sight. The final 3D position is calculated by determining the minimum distance between the two lines of sight of both cinetheodolites. You can see this. This is what is happening here. So you have two vectors, and when you have the minimum distance, it's the position. So that's why you see here that we need two cinetheodolites. Two more phases. We need to generate more points. So we need to generate this the apex of the parachute. So we get this vector from head to the centroid, and we prolongate this vector with 4.25 meters. We know this value because we know the length of the parachute. And also we need to calculate the critical point. What is the critical point? The critical point is the nearest point from the parachute to the aircraft. In this case, what we do is, as these lateral points is not possible to see the same points from the two cinetheodolites, we calculate these points. Okay, so what we do is we need a point of the aircraft. Typically, we use the tail of the aircraft, and we need to build a plane. So we get the track of the aircraft and with this point, and we build this plane. So after, what we do is we build this this vector from the head to the centroid, and also we build this ring. And so the critical point is the nearest point from this ring to this plane. Okay, so that's why we calculate these critical points. And the last phase is the filter. So we apply a Butterworth filter with frequency of 0.15 Hz. And that's all about this process. Once the 3D trajectories have been calculated, the results are plotted. An automatic checker is passed through the results. The objective is to detect main failure during the process. Here you can see the three plots of the three coordinates, and in each plot you have the apex, the critical point, and the paratrooper. So for example, in the Z coordinate, you can check the distance from between the apex and the head. And for example, in the Y plot, you can check the distance between the critical point and the head. In 2016, I did a similar presentation, but using the A400M and with FTI onboard cameras. So now I would like to talk about the advantages and disadvantages of these cameras. Okay, so let me please read this. And first difference. So Cinetheodolites due to the ability of the Cinetheodolites. The complete operation takes more time, and aircraft weight changes more than using onboard cameras. The axis transformation.
So what we did is...
I'm sorry, Israel, I will just pause the video. There is somebody on the call with a loud microphone, which unfortunately I cannot mute. There we go. Thank you very much. I will play the video again now.
Less axis transformation are needed to compare interaction between different paratrooper parachute trajectories. I mean, with Cinetheodolites. When you use onboard cameras, we need to transform to different kind of axes, like the horizontal axis, the body axis. Okay. In terms of accuracy, the accuracy with onboard cameras decreases with the distance between the camera and the paratrooper. With Cinetheodolites, the accuracy is constant due to the similar distance during the jumping. Less aircraft parameters are needed for the axis conversions. In general terms, the accuracy with Cinetheodolites is better. In terms of length, with onboard cameras, there is a limitation about 200 meters due to the separation between the cameras and the paratrooper. With Cinetheodolites, there is no limitation. You have all the time the same distance. Another difference, the visibility. With Cinetheodolites, it is not possible to see the initial jump from one door. The dropping zone. Cinetheodolites are very expensive means, typically over static places, and the availability has to be taken into account. On the other hand, fewer FTI means has to be installed in the aircraft. The exit technique. With Cinetheodolites, it is not possible to analyze the exit technique of the paratrooper that has a high influence in the final trajectory. The exit time. Onboard cameras are needed in both cases to have an accuracy exit time. First time with the paratrooper in the air is taken for the exit time. Let's recap. So I explained a methodology to generate trajectories using Cinetheodolites. Remember these points: to use a CAD software for simulation, to do an accuracy study, to do an image tracking, for example, using Lucas Canad method, to know the photogrammetry for the 3D generation, and to apply image recognition for camera parameters. So on the last important point is the axis system conversion. And just one last advice, yes, that I like a lot, is the divide y vencerás. Thank you very much for listening to me. Any questions?
That's a fantastic video, Israel. I like it very much.
Thank you. It's easier for me.
No, as I think I said yesterday, it's the first time I've been to an online conference with pre-recorded videos, and I think it works very well, provided you're there to answer the questions afterwards. I think it's a really nice way of doing it because it gets around a lot of technical problems which we can sometimes have. So thank you for taking the time to record that and for sharing some photographs, not only of wonderful airplanes, but also wonderful, beautiful places in Spain.
Yeah, I was lost in that place. Yeah, I remember very well.
So we're open for questions, as I said. I haven't received any on the chat, but I actually had two questions of my own for this presentation. I was very surprised at one point it's when you were talking about the different sources of error which you can have in this method, to see you mention that you can have an error of 1.4 pixels. Now, I'm not an expert on visual techniques, computer vision. That's you. How is it possible to have an error of less than 1 pixel? I always thought that was the unitary value, and you couldn't go any less than 1. So how do we get to 1.4?
Yeah, well, it's just to be conservative. It's a value of our experience. When we do this kind of job, in some ways is some part of the job is manual, no? So you have to click in the center of the head. So we see that with different people working in these tools, 1.4 is more or less the standard value. So, but sometimes it's the problem of the quality of the images. Sometimes when we do, for example, safe separation with bombs, we put special stickers, the white, black stickers, you know, and in this, when use this kind of reference, the precision is bigger. So it's less than 1 pixel because we apply zoom and the error is very small. But it's something we have to take into account. But
so it's like it's a calculated mathematical value rather than a physical reality, basically.
Well, it's more an experiment. It's a value from our experience using different people working in these tools. So because at the end you have two cameras and you have to click in the center of the head. So when you see one image, you think that the center of the head is in one place, but in the other image, probably you have a little mistake because it's difficult to interpret the center of the head, for example. So that's why we apply this value to be conservative. But it is better when you have marks in some part. If you put a sticker in the head, it will be better. But it's difficult to put marks in the parachute.
Well, Well, I don't know. Maybe some of the paratroopers would enjoy that. I don't know.
Yeah, it will be
So
better.
I had a second question as well. You took some time to list very clearly the different advantages and disadvantages of using onboard cameras or using the ground-based cameras. I will try and say it Cinetheodolites, which is, you've got a lot of experience of saying it, but I can't manage it as easy as you. I wasn't certain to grasp the conclusion of that debate. Which would be your recommendation? Which is the preferred method to use in the end?
Yeah, well, that depends. I think the best is both of one. You have both, that will be the better, but well, if you have your own aircraft, for example, for parachutists, I think it's better to install cameras on the aircraft, because there are very important information. For example, for us, the exit technique is very important. So if you want to do some kind of recommendations. And so for the first part of the trajectory, the accuracy of the trajectory using onboard camera is very good. So it's better than using Cinetheodolites. But in another hand, if you have to clear, if you have the means, if you have the Cinetheodolites and this kind of means are available, is perfect. But sometimes you haven't Cinetheodolites, you have to operate in a wrong way without Cinetheodolites. So the only solution that you have is the onboard camera. So it's depending. You have both means, and you have to choose one of them.
Yes, we talked yesterday about how you sometimes have to use different tools for similar problems according to the specific case. Do you have any experience of blending the two, of combining the two? So starting the analysis of the trajectory from the onboard cameras and finishing with the view from the ground?
Yes. This is very interesting. Yes, what we have done in the past is we use both methods to validate one against the other. Because we calculate a trajectory using onboard cameras, and we compare the same trajectory using the Cinetheodolites, and it is very interesting to validate the methodology.
Do you have to have some kind of communication between the ground systems and the flight systems to make that work, or is it all post-processing work?
Yeah, it's all post-process. The only thing that is very important that you get a well tracking thing, and the images with the best quality. For example, when you use Cinetheodolites, you have to wait the paratroopers, because you can just track one paratrooper at the same time. So you have some limitations. When you are using onboard camera, you have less limitations in terms of operation. You can launch people with more frequency. When you are using Cinetheodolites, you launch one paratrooper, and you have to wait maybe 5 seconds to the next one. So, well, you have to see what could be the best for the flight test campaign.
I suppose if you had unlimited resources, you could presumably have lots and lots of Cinetheodolites on the ground and do bigger passes. But that's a very expensive exercise. So.
Yeah, that's right. But if you have both of the system, it will be better. It's like when you are using a LiDAR, cameras, EMU, inertial. The best is to have all of the sensors.
Okay. A question has come in from Paul Cox, and he's wondering more about the practical organization of the test. When you are doing these tests, do you need coordination or a communication coordination between a crew on board the airplane and the people on the ground, or are they running as two separate organizations?
Yes, well, it's not part of my job. There are other people working on that, but yeah, of course, they have to be very coordinated. Typically, there is an operator for the Cinetheodolites for each of them, and you have to track manually. But after is more or less semi-automatic. You select the objective, and after the tracking is automatic. So, but at some point we have lost some parachutists because the tracking is lost, for example. But you need to know at the end the aircraft is doing some circuits and jumping. So yes, you have to be very careful to avoid losing the tracking.
Okay, and talking about tracking, another question which has just come in from one of Paul's colleagues from the NLR. He's wondered if there has been any studies or any tests done where the trajectory is measured using an IMU. I must confess I'm not familiar with the term IMU. I presume it's an
inertial. It's an
inertial
inertial
measuring unit. Yeah.
Yeah.
So
Yeah,
do you have any
it's a good,
experience of that?
yeah, it's a very good question. We have applied this kind of technology, but in another kind of things. For example, when we calculate the trajectory of a load. But in this case, the problem is that to calculate the trajectory of a parachutist, we need 3 points: the head, the critical point, and the apex. The apex is the center of the parachute. In this part of the parachute, it's impossible to put an IMU. So we can put an IMU in the chest or but we get just one point. But for us, we need 3 points, because with these 3 points, we build a volume of 16 spheres. And with this volume, we calculate the interactions with another parachutist. So we calculate the conflicts, the crossover, we say. If we have a conflict with this kind of, it's a geometry, so that's the problem. We cannot install IMUs in the parachute.
Yes, not without fundamentally affecting the way the parachute would fly, of course. So that would be the issue. I understand. Okay, well, the answer has been well received and understood. So thank you for that.
Okay.
I must confess, I have driven alongside the drop zone at Fonsorb many times on my way to and from the office. It's on my route to and from home.
Yeah, very beautiful.
Yeah, it's lovely, and I've very often seen the aircraft flying there and always wondered what they were doing. And so now, thanks to your presentation, I have a better understanding of that. I know you're not doing all of the trials they do at Fonsorb, but now I understand at least a part of them, and why the aircraft are flying so many circuits. Because when I'm not driving that road, I sometimes go flying and I see the aircraft using this airspace, and I always wondered why. So now I know.
It's a beautiful place, and they have a zoo near the place, and they have some problem with this because they get up the elephants and the tigers very soon. Yeah.
There we go. We never thought we would talk about zoos in an SFT conference, but we just did it. So thank you.
Okay.
Well, thank you once again for your presentation. It was a very interesting one, and supported by some wonderful images to show us the practical side of your technical background. So thank you very much for that.
Thanks, Jim.